how you tell, essentially, okay, if you have an electrolyte or not, is by sticking 2 electrodes in the solution and then seeing if the light bulb lights up, okay? Because if it lights up, then you have electrolyte. So there are 3 kinds of electrolytes that I need to mention before we get a little bit too much into it. Strong, weak, and non. Last time I mentioned to you that when you have electrolytes, the way the electrolytes work is that if you dissolve something in water, and this is an aqueous property, right? So if you dissolve something in water, it undergoes a process called hydration, okay? And that hydration will cause dissociation of ions, right? So, which means that electrolytes have ions, which is why they conduct electricity, all right? So when we're talking about electrolytes, in a strong electrolyte, then you would have a lot of ions or less of ions? A lot of ions. Okay, so you should have a lot of ions in the strong, a little bit less in the weak, and absolutely none, okay, in the non-electrolytes. Do you have this worksheet that I gave to you? If you do, please take it out, okay, because I'm going to go through some of these things. I gave this to you last time. If you were not here last time, wink, wink, you know who I'm talking about. So if you want to come up and get this, it's fine. You're most welcome to. I still have some here. There is one error in there. I don't know if you noticed that already or not, but the first chemical in here is ammonium hydroxide. The second one should be sodium sulfate. And if your nomenclature is serving you right, it should be Na2SO4. Thank you very much. Okay, so there was a little error there, a typo. Okay, very good. So when we talk about strong electrolytes, it means that you have ionic compounds.
Na2SO4.
And as I said last time also, for any kind of ionic compounds or any kind of compounds, you should be able to distinguish whether they're ionic compounds or molecular, right? And the way you tell that you have ionic is metals and non-metals, okay? So those are your ionic compounds. The other example for strong electrolytes are going to be acids. And these are a little bit weird because acids, as you know, have no metals in them. Okay, so for example, hydrochloric acid, and you may want to write aqueous there so you know it's not hydrogen chloride, but hydrochloric acid. Sulfuric acid. Acids don't have any kind of metal in them. They don't seem to even have any ions in them, okay? But they are very strong electrolytes. And the 3 classifications I gave you for the reactions, precipitation, neutralization, and redox, when we get to each of those, then I will explain a little bit more on these, okay? But right now, just write as it is. Okay, so ionic compounds, acids, and then also bases. And in this one, it's more specifically the metallic bases, and metallic bases meaning any bases that have metals in them, like sodium hydroxide, calcium hydroxide, any hydroxides that have at least one metal in them. And I know you can classify them as ionic compounds also, which is fine, but they're also categorized as bases. Okay, so these all will be considered strong electrolytes, which means that they conduct electricity very well. Okay, all right, going on to the weak electrolytes, these are the hardest ones because it's very hard to judge at this point for you whether something is going to be strong or not, or weak or not, because it's a little bit unusual. So I'm just going to give you some examples over here. Ammonium hydroxide and acetic acid. These two are considered to be weak electrolytes. When you have a strong electrolyte, the whole point of a strong electrolyte is that you have many ions in the solution, okay? Which means that when you dissolve something in water, it should completely dissociate to give you 2 things or 3 things, okay? Whatever it is. What happens in the weak electrolytes is that dissociation is not complete, okay? And for you to tell right now which is going to have a complete dissociation and which is going to have an incomplete dissociation is a little hard, okay, because we're not there yet. So just take my word that you'll have maybe 2 or 3 categories here for now, okay, with the weak electrolytes. The non-electrolytes are very easy then. These are going to be the molecular compounds. Molecular compounds, of course, don't have any ions in them then. Okay, so if you can, just go through your sheet over here with me, and let's do a couple here. Now, this is actually your self-study, which you can probably do this weekend. Okay, after you finish studying for the test and you finished your homework, then you can start working on this. Okay, but right now I want you to answer some questions here with me. So NH4OH, where would you put that? Is electrolyte or non? Just electrolyte or not? Not even weak. Electrolyte, right? Good. Okay. Next one.
Electrolyte.
And CO2, carbon dioxide?
None.
Non-electrolyte. Do you feel comfortable? Do you see how that works? Okay, so you look at the compound, look at the makeup of it and all of that. Okay, that's how it works. So this is about weak and strong electrolytes. Very good. Okay, now let's go on to talk about the first classification of reactions that we started, and that is precipitation. And actually, as usual, before we get into precipitation, I want to talk about one other thing. As usual.
This would be one. I think it's a week.
And sometimes I can't find the right word, so I just write something just so that you know what I'm thinking about. But I'm sure there is a word for it. Okay, but how do you know that a chemical reaction is taking place? Okay, because then you have solubility, where you have salt dissolving in water, which also gives the appearance that something is happening, right? Something is happening because your solid went into a different state. Okay, so something happened there, but you, because you've done some of these things, you knew it was a physical change. Okay, there was not a chemical change. So if you were to think about chemical changes that happen, or if you were to think about, well, was this a reaction? Was this a chemical change, or was this a physical change? So how would you look at those things and categorize them? Or how would you know that a chemical reaction took place? Any clues? There are four. Okay, I'll tell you one, then maybe you'll come to the other ones. Precipitation. Yeah. And precipitation is when you form a solid as a product. Which means that you mix two solutions together, okay? And then if you see something solid forming right away, then you know something is happening. Okay, and there's a chemical reaction. And remember, the whole thing about a chemical reaction is that they are irreversible as such. You'll have to do another chemical reaction to get them back, okay? And so, well, the critical one here is precipitation reaction, very obvious, okay? The second one is what we call effervescence. And this really is gas formation. So when you add two solutions together, or two things together, and then you form a gas, there's a gas evolution there, it's called effervescence. So then you know it's a chemical reaction. And of course, I'm pretty sure you have done this in your 5th grade maybe, or 4th grade. You made a volcano? Mm-hmm. Yes, science fair, maybe. Mm-hmm. Yeah. I don't know how many volcanoes I saw when I was in elementary school science judge. I was like, oh my God, okay. And each one better than the other one. So gas formation, that's your typical, very typical kind of a gas formation, okay? So precipitation, effervescence, and then there is heat changes. This is a little bit of an iffy one, okay? Iffy in the sense because sometimes it's a little bit hard to judge, okay, as to what's going on. Some things are very, very clear. Like when you add two things and suddenly you have this really hot reaction in there, okay, which means that you really clearly see the change in the temperature. The change in the temperature can be two ways. It can either go really hot, it can either go really cold, okay? And if you've ever bought any of the hot packs or cold packs, then that's what this is, okay? And some of the hot packs actually are not reusable. Once you use them, they're done, okay? And the cold packs, so there are different kinds, okay? There are things that you can put in your microwave and then heat them up again, use them up again, okay? But there are things that you can't use again also. So the ones you can't use again, those are the chemical reaction ones, okay? And so heat changes, there are two kinds, what we call endothermic and exothermic. And endothermic is, gets cooler outside, and then this is something that gets hotter. So for example, if you're doing this in a test tube, then the test tube is going to get colder when it's endothermic, and it's exothermic, it means that it gives out heat, and so that becomes hotter, okay? All right, and the last one is evolution, sounds very scientific, of light, which really is what we call chemiluminescence. Such a big word, if I get the spelling right. Yeah. Chemiluminescence. Which means that when you mix two things together, you have evolution of light, you have light coming out. And again, if you've gone to any fair or any of the amusement parks or any show at night, you get those things, those sticks or those necklaces which you break, and then you have light coming out of it. Total waste of $5, as I say, but you know, that's what it is. Okay, and so that is chemiluminescence. Again, that happens one time and then you're done, right? It doesn't happen again. You can slow down the reaction, okay, by keeping it in the freezer or something. Anyhow, these are your 4 ways that you can actually tell that you have any kind of chemical reaction going on. Okay, they all have short terms as well. So for example, for precipitation, you can use PPT. For effervescence, you can use EFF. For heat change, the endo and the exo. Okay, so you can just use endo and exo, okay, for these two. And evolution of light, chemiluminescence, I'm very sorry, that's the only place where you'll see it. We don't do any of these reactions over here, and we don't have a short term for this either. Okay, so you can just
the only one that really needs it.
This one?
It's the only one that really needs it.
It needs it, I know, that's true. So anyhow, and the reason I went through this also is not just because it's part of this chapter, but also you have a lab on this one. Okay, so a week or 2 from now, you will have a lab where you're actually looking at all of these different kinds of reactions. It's really one of the funner labs that you have. I know watching the crucible dry was really something really impressive, you know, you're just waiting for 7 minutes to occur, you know, and then it's okay, fine. But this one is an interesting lab that's coming up in about 2-3 weeks, okay? All right, any questions about this? Yes?
The lab we did with magnesium oxide, would that be considered evolution of light or heat change?
Well, it depends. Did you see the light?
Yes.
You saw it? Okay, yeah, a lot of my students didn't see it. We have it covered.
Well,
Okay.
because our professor, like, lit
He
one
did a
on fire.
demonstration, so we
Oh,
saw it. but
Vladimir is so much fun. Oh,
in
yes,
the
he
crucible,
is.
you
Yes,
couldn't
yes.
see us.
Okay, yeah. So, yeah, that is actually chemiluminescence.
Okay.
Yes. And so that reaction is actually also coming up. So my students, I'm sorry, okay, don't listen to her. It was not that much fun. It's much more fun when you do it in 2 weeks, okay? So it is coming up, all right, and we will do it. Okay. All right. Now we'll go on to precipitation reactions. Again, this is so much nicer when you see it, and I'm really sorry I didn't bring everything today because issues. But anyway, I will show you some of these things next time. In precipitation reactions, you have things that are not soluble. That's why they precipitate out. That's why they form a solid. And you have to appreciate yourself also that when you jump into a pool of water that you don't dissolve in water, okay? Which is really great, okay, for your mom, for everybody, okay, in fact. So you have to understand that there are differences, okay, between your body and the water, okay? That there is a reason why you're not dissolving in water, all right? However, there are things that dissolve in water. On the other hand, you can go to the beach and you can walk on the sand and the sand is there, which means the sand is not dissolving in water. So there are things that don't dissolve in water and there are things that dissolve in water, okay? And so you have to kind of figure it out, and some of these things take a long time, some of these things not so much, okay? So for us, our precipitation reactions are going to be based on anything that is and not soluble in water, which is also ionic, okay, that we're talking about because we're talking about aqueous reactions here. Okay, so the molecular compounds, we don't talk about that here, okay, whether they're going to be soluble or not. But how do you tell that something is not soluble in water? And for that, you have this beautiful table, okay, which you can use. And just like the polyatomic ions, I'm very sorry, this is also one of those things you have to just sit and memorize, okay? And you should be happy it's not for this exam, it's for the next one, okay? So at least for this one, you can still focus on your polyatomic ions and leave this one for next time. The one that I've given to you in the chapter summary is a lot better than this one, by the way, okay? Because this one, there's a lot more words. In mine, I've tried to make it a little bit clearer for you, okay? A little bit easier to remember as to what is going to be soluble, what is not soluble, okay? Otherwise, why is it that sand is not soluble, whereas sodium chloride is so soluble? And that goes with the rules, okay? So, all soluble, okay? Things that have absolutely no exception whatsoever, okay, is alkali metal salts. And when we say salts, what that really means for us is that we're talking about ions. I'm not talking about alkali metals as in sodium and potassium. I'm talking about the alkali metals as in sodium ion and potassium ion. Okay, so you have to clarify that. Don't just say alkali metals, okay? It's going to be the ions in there. So all alkali metals like lithium ion, sodium ion, potassium ion, what does that mean for us? Lithium ion does not exist by itself. Okay, lithium ion will exist only when there is an anion with it. Okay, so whether you have lithium chloride, lithium nitride, lithium sulfate, lithium sulfide, lithium oxide, it doesn't matter what the anion is. But if it is combined with lithium, it's going to be soluble. Okay, that's what it means. And this is all soluble, no exceptions. And that's the good part. When you have no exceptions, then it's easy to remember stuff. Okay, it's harder when you have exceptions. So alkali metal salts, all soluble. The other things are ammonium salts, and ammonium salts, which means NH4 plus. NH4 is the ammonium ion, which is the polyatomic ion.
So Dr. Gupta,
Yes.
if you see lithium to like any of them in the first group and with something else, you automatically know that it's soluble.
Automatically. No exceptions. Okay, that's why I gave you the examples. That could be sodium hydroxide, potassium sulfate, whatever. It does not matter. Okay, all right. And then we have nitrates. NO3 minus. So nitrates could be with anything, whether it's calcium, potassium, iron, ammonium. Ammonium itself has no exceptions whatsoever, so we have double no exceptions there. So all sorts of nitrate salts are going to be all soluble, no exceptions. And then we have acetates here. All acetate ions, salts, will be all soluble, completely, no exceptions. These are the easiest ones, by the way, okay, because as soon as you see these ions present in any substance, okay, then it automatically, it's all fine. Okay, now I'm going to bring in some exceptions over here. So now halides, and when we say halides, that means F minus, chlorides, bromides, iodides, any of the halogens. Those are called halides. As you learn more and more about these elements, you will realize that each group is very special in its own way. Okay, and they have very unusual characteristics. So halides, all of these are soluble except. Now we have exceptions. And it's the exceptions that always kill us. It's never the simple and straightforward stuff. Okay? And so, except for lead, silver, and mercury. Okay. I'm not going to write out all the rules because I just wanted to give you some examples of how this works. Okay? Well, what's up, Jacqueline? What happened?
No, like I get the exceptions, but are they considered halogens?
No. Halides are all soluble. So you have potassium chloride, calcium chloride, all soluble. But if you have lead chloride, that's not soluble. That's what it means.
If it's combined.
Right,
with,
if it's
okay,
combined
okay.
with these, okay? So for example, PbCl2, not soluble. Okay, PbI2, not soluble.
I know.
Okay, good, I'm glad we clarified that, okay? But that's what it means. So exceptions meaning that if you have halides combined with any of these three elements, okay, then you will, then it will not be soluble, then it will precipitate out.
Do we find out the reason why, or is that a GenChem2 thing?
No, it's not really quite a GenChem2 thing. It's just a property that some substances have. Okay, there is no mystery to it. Okay.
HGZ.
Is there any way to separate them other than
HG.
like? Is there any chemical reaction you can combine on those two things to separate them out?
What do you mean separate them out?
Like so that they're not. So it's not Cl like PbCl2. So it's like just Pb and then Cl.
If you're trying to separate the ions out, yeah, sure, you can do that. Okay, that's not a problem. But if you're trying to say, is there any way that you can make lead soluble in water?
Yeah.
Yes, you can, because if you combine lead with nitrate, it's soluble in water. Okay, because nitrate has no exceptions, okay, whatsoever. So lead nitrate will be soluble, but then lead chloride is not soluble. Okay, so yeah, it depends how the combination works, okay? All right, so I'm not going to write all the rules because the rules are written here for you. The rules are written here for you also, okay, in your chapter summary. So all you have to do is kind of memorize them. Let me just go over them with you a little bit. So halides, I gave you the examples. Sulfate, again, if you have your PowerPoint or if you have your chapter summary, please have that in front of you or the textbook. Sulfates are all soluble except for strontium, barium, lead, and mercury. And the reason I'm saying these is because I want you to see a pattern in this, okay? Then it's the other way around. That means everything is now insoluble except, okay? So first things that I mentioned over here are all the things that are soluble except things that are not soluble. And then the other column is generally for things that are all insoluble except. Okay, so let me give you an example of that. Let me just finish this one. There's only one left anyway. Okay, so sulfate, SO4. These are usually all soluble except strontium, barium, lead, and mercury. That's it. That's it for the exceptions for solubility. So now it's the other way around.
On the, it says Ca and Ag as well. So silver and calcium are all soluble.
Calcium and sulfur for sulfates. Okay, good. Let me write that too. No, it's okay because I had to change this one. I still have the old one.
Okay.
Yeah. So calcium and silver.
Yep.
Okay. Yeah. Yeah, I had to. You have the latest one. I have the old one. Okay. Then all insoluble, and what I did in my chapter summary is I just put them in the insoluble column. So which means all carbonates are insoluble. So CO3 2 minus, that's the carbonate. That's insoluble. Okay, Malik, except for what? Except for what? All carbonates are insoluble, except
Lithium, sodium, potassium, rubidium, cesium, and ammonium.
Malik. Did you change your name? Okay, not yet. Okay, all right. Thank you, Anthony. So which one was it again? I was thinking of lithium.
Lithium, sodium,
Very good.
potassium.
Okay, very nice. So carbonates combined with alkali metals and ammonium salts. Okay, those are the exceptions, and they're exceptions because they're always going to be soluble. Okay, so it's not really an exception. Okay, in certain ways if you think about it. So that's what these insolubles over here are, and then you have phosphates, hydroxides, and sulfides. Okay, which are also all insoluble, except when they're combined with things that have no exceptions there. Okay. All right, these are rules that you just have to memorize. I'm very sorry, there is no other way, okay, to do this. So one of the questions that I usually give you is kind of what is question number 3, okay, in over here. And question number C says use a solubility rule table, and you can use the table here, okay, we're fine, to say if the compounds are soluble or insoluble. Okay, so strontium carbonate. Strontium carbonate, how do you approach the problem? You look at carbonate, and strontium is not in the exception rules here, okay, with all soluble. So you don't look here, you look at the carbonate, and carbonates are supposed to be all insoluble, except for those things which strontium is not there, so that means strontium carbonate is not soluble, okay, insoluble then. Magnesium sulfate, insoluble then, okay, because sulfates are supposed to be over here, okay, all insolubles. So that's how you would answer these questions. You will choose whichever one. Let me go on to silver nitrate, which we just answered here also. So down the table, and silver nitrate. So you know that nitrates are all soluble without any exception. So that's it, okay? All right. I have a few hints here for you, okay, to help you remember this, all right? And the hints are that a lot of the insolubles that you have, these are all polyatomic ions if you look at that, carbonate, sulfates. The sulfide is an unusual one, okay, because sulfide is not a polyatomic ion. So a lot of those insoluble ones are the polyatomic ions. And then the insolubles over here that you see, a lot of these are what we consider to be heavy metals, okay. Heavy metals have a lot of mass, okay, which you can see silver, gold, mercury, lead, okay, these are what we call heavy metals, and these heavy metals will precipitate out, okay, in those cases, so that's where the exception is. And then you also have group 2, calcium, strontium, barium, okay, group 2 is also quite insoluble, okay, for a lot of things. Now if you think back to your chapter 2, we said group 1 was called the alkaline metals. Group 2 is called the alkaline earth metals, okay? And there is a reason for the earth metals is because a lot of the earth things that you find, the soil, the rocks, they're actually all made up of these things because they're insoluble in water, okay? And it doesn't mean that they don't dissolve, they dissolve very slowly, okay? Yes, Jake?
You said magnesium sulfate is insoluble?
Who's going to be insoluble?
I thought sulfates were all soluble.
No, sulfates are not here. Oh, the exception is not there for magnesium? Did you check the latest one?
Yeah, it's not on there.
It's not on there? So magnesium sulfate is soluble then. Okay, good. All right, so if sulfate falls over here and magnesium is not here, then you're right. Okay, it's going to be soluble. Okay, Caitlin, thank you very much. All right. Good point. All right. You did talk about magnesium sulfate. That's there. Okay, very good. That's how you approach the problem, okay? And just because I said something doesn't mean it's always going to be correct, right? You can always correct me if you have doubts, okay, about something, because I think I should go ahead and print out the new stuff. That would be good for me if I'm updated, okay, in my thing. Okay, so now what we have to do is write out some equations and see if you can actually predict things in equation format. I'm going to stop right here for a second. So this is going to be precipitation equations. And if you look back to the last class, the precipitation equations are what kind? Single displacement, double displacement, decomposition, synthesis, how would you classify? Double displacement. Okay, so precipitation equations are double displacement. What you will have to do, okay, is you will also have to be able to predict the products, and because I'm telling you over here at least that this is a precipitation equation, we'll go ahead and write the products ourselves, okay? And doing the double displacement. So the way you do the double displacement is you take the cation of one and the anion of the other. And then the other way, you take the anion of the first one and the cation of the other. So the reds will go together, the blues will go together. When you form the product, on the product side, your formula should still be correct. If your formula is not correct, again, your equation will not be balanced. Okay, so your formula still has to be correct. So let's combine silver with chlorine. So silver chloride, and then sodium with nitrate. And again, going back to chapter 2, when you write your formulas, please make sure that you always write the cation first, okay? And then the anion. Always positive first and then the negative, or always whatever is on the left-hand side of the periodic table, that always goes first. So even though when you're writing NaNO3, it should not be written as NO3 and A. Okay, that's not the right way. So make sure you write the cation first, okay, and then the anion. So this is not correct. Some of you did this in your pre-labs. If you remember, you were supposed to calculate the empirical formula, okay, for this one in the pre-lab. Some of you actually wrote it like this, okay, and I was wondering if, and I forget now, okay, whether it was my students or somebody else's, but you have to remember to write always the positive and then the negative, okay, always like that. So with these also, write the correct thing. The next thing to check is the formula correct? Is it correct? Yes? So 1-to-1 ratios, okay, for everything, because it's marked +1, -1, +1, -1. So luckily we are all good. That's the first thing to do. Second thing to check the formula. Third thing to write is whether something is going to be aqueous or precipitate or gas form, or what is that, okay? And so now your rules will come into play. So silver chloride is going to be a solid. This is going to be aqueous. It has double advantage of having sodium and then nitrate also. Okay, so both of them are completely soluble. So we're all good to go. Good? This equation, very simple equation, precipitation equation. Okay, that's what they're called, because here you have aqueous, and by the way, everything now for you has to be either aqueous, solid, gas, liquid. You have to indicate those things. If you don't, then your equation is incomplete. Okay, you will not get complete grade for it, so please make sure you write things out. Okay, let's try another one. Sodium sulfate and go ahead, write the products out. These two are aqueous. Sodium will combine with
PB lead.
Sodium will combine with nitrate. Positive with negative. A cation and an anion. Okay, not two cations together. All right? And then, of course, you will have the anion of one and the cation of the other. Okay, please be careful. Yes? No? Okay.
If sodium nitrate
Sodium
solid
nitrate.
is nitrate. Well, SO3 is nitrate, isn't it?
SO3 is,
No, that's SO4, sorry.
okay.
It's aqueous,
Mhm.
but PbSO4 would also be aqueous.
Is it?
it says that sulfates, SO4s.
All soluble
Except-
except.
Oh, except, okay. I was thinking all insoluble except for Pb, okay.
Okay.
Fine.
So then we have NaNO3 and we have lead sulfate. Our formulas are fine? No? Zachary, what's
You
up?
need-
I need to balance the equation? So the formula is okay. Okay, the formula is okay. I need to balance it. Okay, that's all. Because this is +1, this is -1, +2 and -2 over here. So yeah, 2 sodiums over here and 2 nitrates here, so 2 there. Good. Okay, so equation is balanced. Aqueous or precipitate for sodium nitrate? Good. This is precipitation equation. Yes, Max.
How do you determine whether it's aqueous or
That comes from the solubility rules. Yeah. In the beginning, I would advise you to just have a cheat sheet with you. Okay, so write everything on an index card and keep it handy. Eventually, you're going to have to memorize them. Okay, everything, all the rules, but hopefully with practice it will come. All right? Yeah. Okay. These kind of equations, by the way, that we have just written out, this is called a molecular equation. And a molecular equation is just that, which means everything is neutral, electrically neutral, everything is written in a compound format, and it gives you everything that you need in that equation, which means that it tells you whether something is aqueous or solid and what the coefficients are. Okay, I mean, so far we've been dealing with molecular equations. Okay, we just never put a formal term to it, but everything that we've done is molecular. Now what we're going to do is take it one step further and give it an ionic equation too, because now we're dealing with ions because we're working in an aqueous system. So all of these are not like this at all, okay, when you actually have them in a solution. So if you have a test tube or a bottle full of sodium sulfate, that's not how it is. Sodium sulfate actually will exist as like this in that solution. It's not sodium sulfate. Okay, and that's why I was trying to explain the concept before as to when you take sodium chloride and you dissolve it in water, it dissociates to give you sodium ions and chloride ions, and that's exactly what I'm talking about here. But is this correct, or do I need something else? Two what?
Sodium.
2 sodium? Okay, and where do I write the 2? Do I write the 2 here, or do I write the 2 here? First one, second one? Everyone, Kathleen? Yes, I know. So which 2? Because this is Na2SO4. So where should my 2 go? Should my 2 go over here as a coefficient, or should my 2 go down here as a subscript? So which number is correct, 1 or 2? Everybody together?
One.
Okay, thank you very much. You can't have Na2 because that would mean you have diatomic, right? That's what it means. Yeah, so you can't have diatomics like that. So when you have 2, it means you have 2 moles of sodium ions, 1 mole of sulfate ions. That's how we've been trying to learn all these things. So here are the 2 moles of sodium ions and 1 of sulfate. We're not done yet. There is one more thing to write, and that is aqueous. I have to say ionic equations are a little bit of a pain in the behind. Okay, maybe I'll have to edit that one later. Okay, but in any case, they're a little bit pain in the behind because you have to explain so many things here. Okay, and so here we have lead, and lead is going to be 2 plus and aqueous. Nitrate, you have 2 of nitrate ions and also aqueous. Again, please do not write this. That's wrong. Do you see that? You just can't take this out separately and say this is minus or 2 minus. You can't do that, okay? Because essentially what you have here is 2 of the nitrate ions, okay? So you have to separate that out like this, okay? So nothing of this sort. And then on the right hand side, we have the sodium nitrate as aqueous. So 2 sodium ions, again, aqueous. 2 nitrate ion, aqueous, but the lead sulfate is not, so we have to write that as solid. That's not aqueous. Lead 2 sulfate is not aqueous. Okay, this is what we call an ionic equation. And the last one we're going to write is called the net ionic equation. Little time consuming work, but it's really quite easy once you know what you're doing. So in the net ionic equation, what you do is you look at your ionic equation and then you cross out the ions that are on both sides of the equation. Okay? I usually start on the right hand side. Okay, on the right hand side I have sodium ions. Do I have sodium ions here? Yes. Okay, so I will cross that out. And then I have nitrates on the right hand side and I have nitrates here also. And because my molecular equation was balanced, hopefully all my ions will be balanced too. Okay, then I don't have to worry too much about that. And then I have sulfate and lead left on the left hand side, which is aqueous, and we don't have those ions on the right hand side. So then my net ionic equation is SO4 2 minus aqueous plus lead 2 plus aqueous to give us lead sulfate. No brackets. I don't know why I have brackets there. You don't need a bracket there. Okay. Solid. And that's the net ionic equation. The net ionic equation shows you exactly what the chemical reaction is that's taking place. The ions that you have crossed out, this and this. These are called the spectator ions. And spectator ions mean that they are still there in solution, they're just not doing anything. Any questions? Yes?
On the ionic equation, you can separate the lead sulfate?
You can't separate it because it's a solid.
Oh,
Yes, you will separate only things that are ionic. Okay. Few things to keep in mind when you do these equations, okay, is first of all, you should know your nomenclature well, okay, because sometimes this is not how I give it, this is how I give this equation. That's how I get the equation. Okay, so which means that you have to take the name and give it the formulas.
Should that
All
be
right.
nitrate? What you
The
meant,
2 nitrate, yes, thank you. So you have to write the formula yourself, first of all. Second thing you have to do, you have to predict the products, okay, which now you know the technique, which is double displacement. Okay, you have to do double displacement for precipitation reactions. That's the second thing. The third thing you have to figure out is anything going to precipitate out. Just because I wrote something out does not mean that it's going to precipitate. Okay, because part of the question can also be, what kind of a reaction is this? Will you see any precipitate? Okay, so that's the third thing, that you have to figure out if something is a precipitate. And then the next two things are writing the ionic equation and the net ionic equation. Okay, so it's really quite an involved process. Okay, so let's try something out here. And let me give you just a molecular equation first. Go ahead and write this, and write the products that you think you'll form. And you don't have to write the names of the product. Go ahead and convert everything into formulas. If you've written the products out, then go ahead and write if anything is going to be a solid or not. The products technically for this one should be sodium sulfate and potassium chloride or chloride. And make sure your formulas are correct. As I was walking around, I saw KSO4. It should be K2SO4 because SO4 is 2 minus. And then this one should be an A2SO4, which means my equation is not balanced, okay, at this point. So 2 here, and then 2 here. So now my question then, or my task is to figure out if I form any precipitate. Do I form any precipitate? No, I don't. Okay, because both of them are alkali salts and both of them are going to be aqueous. Okay, so this is really one of those reactions where you mix two things together and you're just waiting for something to happen. Nothing happens. Okay, it's just, yeah. So it's just one water mixing with another water, and like, what? Where is the magic? There is no magic. Okay, so it's one of those things. All right. Yes, George.
So you wouldn't really ask us to find an ionic equation for that because you cross everything out.
Everything is going to cross out. Yeah. So essentially, a question like this would be for you to predict if there is any precipitate or not. Okay, not to write the ionic equation because yeah, that would be a waste of time. And by the way, even if I am asking you for an ionic equation for this one, there is none. Okay, for this. You can write the ionic equation because everything is in ion form. Okay, that's not a problem, but there is no net ionic equation for this. Okay, all right. So this is what we call the precipitation reactions. And equation number B, okay, that you have here, 5B. That's what I have here for you, okay? On the website, there is one worksheet there for you, which has 3 pages in it, okay? And those 3 pages have a lot of equation writing in there, okay? So you may want to print that out eventually, okay, and practice these equations. They're very good for nomenclature also, but that's kind of what you have to do anyway. All right, so question number 4 is an easy one. Question number 4 I didn't go over at all, so let me just go over that a little bit. Is that what kind of ions do you form when you have all these things in solution, okay? And the kind of ions you form, that's exactly what we're doing over here, okay, with this. Is you take any kind of a compound, and if you have it in water, how will it dissociate? And trust me, the mistakes that I see are very typical mistakes, okay? Like, suddenly you will forget, okay, when you're writing this one out, and trust me, you will do this for me. I know you will, okay? It's a very common mistake to forget to write this. This is how it should be written, not like that, okay? This is the correct way. But somehow we forget those kind of things when we're writing and doing these equations, okay? So please make sure that you take your subscripts and make them coefficients, okay, as you're going through these equations. Essentially, that's it about precipitation equations. Is making sure you know your solubility rules, writing all these equations out, okay, and then writing the net ionic equations. Okay, that's your precipitation reactions. Go over some more examples in the textbook, okay, and otherwise, because now I'm going to go on to acids and bases. Do you have any questions about this? We're okay? All right, yeah, again, this just comes from practice and memorization. Okay, and we're not done with equations. We're still going to write more. Okay, so we'll practice more.
So according to solubility, we figure out how to find something that's aqueous or something that's solid. How
Yes.
do we find something that is a liquid or something that is a gas?
Right, and that's coming up. Okay, yeah. Because for precipitation reactions, yeah, no, the precipitation reactions are only for the precipitate that's forming, which is only for the solid. Okay, yeah. The other categories we have, that's where the other ones will form. If we are clear, move on. Moving on. What you learn in the precipitation equations is actually a very fundamental thing. And so you just carry that on to the next equation. So it becomes a little easier as you go on. The second reactions we're going to talk about is neutralization. Which are the acid-base reactions. In acid-base reactions, the first thing I want to do with you just a little bit is to tell you the properties of acids and bases, okay? Because acid and base is a category of chemicals that we talk about, but what is it that makes an acid, okay, or a base? A base The simplest one that you know is that acids are proton donors, okay, which means that they give H+. They all have hydrogen ions in them, and we didn't talk about ions so much yet, which we will, but they all have hydrogen in them. Whether you look at HCl, H2SO4, HNO3, whatever it is, it starts with H, okay, and so they have hydrogen in them, all right? And right now, the acids you will be dealing with, all of them have have hydrogen as the first element, okay, in there. Not the last one, the first element, okay, in the formula. So they are proton donors. The bases that you know, they're all supposed to be what donors? What do they donate? The bases. Hydroxides. Okay, thank you. Hydroxides. So potassium, sodium, ammonium hydroxide, all of these are hydroxides. Example, HCl, example, NaOH. Please remember, this hydrogen is not the same as this hydrogen. These are different things. Okay, so your acid protons are always going to be written first. Okay, and you have to recognize the hydroxide as a polyatomic ion as hydroxide. Okay, yeah.
Is that because in the acids the H is positive and then
It's positive.
the
We
bases
talked
it's
about that
negative?
before. Yeah, yeah. We did talk about that in chapter 2, that in acids, all your hydrogens are positive. Okay, protons, that's why it is. Yeah, very good. Reminds me, look at question number 1. Look at question number 1 in the self-study, and there is this formula given to you, okay, which is actually methanol. It's a covalent compound, right? Do you think, would you classify this as a base? Okay, first of all, would you classify it as an electrolyte or a non-electrolyte? When you don't all answer, I know there's confusion, but that's what I want to clarify over here. So, non-electrolyte, non-electrolyte. Do you want to just raise your hands? Don't be shy, just go ahead and raise them. It's okay, I'm not taking any big polls. Non-electrolyte, non-electrolyte. Okay, electrolytes. Look at all these non-deciders. You know, next year we have to vote, right? We're back to the polls again. So you better start learning how to vote. Okay, so this one, non-electrolyte. Yeah, so the people who spoke up, good for you. Okay, this is a non-electrolyte. And how did you decide this was a non-electrolyte, Jacqueline?
I could totally be wrong, but I recall you saying something from the first group paired with silver.
That should be the only thing that's ionic, right?
Yes.
Yes, very good. And that's
Okay.
it. That is it. All right? All right. CH3OH, if you look at all the elements in there, those are all non-metals, right? Is any of them a metal? No. So which means it's a molecular compound. If it's a molecular compound, then it is going to be a non-electrolyte. Okay? So you have to be able to recognize the difference between an acid and a molecular compound, because acids are also all non-metals, but acids will have this proton right in the front here. Okay? And that's how you differentiate between the two. Okay. That's the first thing that you know, chemically speaking, that acids are proton donors, bases are hydroxide donors, and that's actually one of the first definitions of acids also. You will learn more definition of acids and bases in GenChem2. Okay, right now we're just doing some basic properties or acidic properties. I don't know. Okay. Then, you got the joke. Okay, somebody got it. Did you guys get it? No. In any case, going on here, acids are generally going to be sour, okay, in taste. They're going to be sour in taste, and bases are going to be bitter in taste.
So we should just start sticking them around.
No, that doesn't work. But you do encounter acids and bases in your life all the time. So examples of acids are, of course, all the fruit juices. Okay, that you have, those are all acidic. And bases you don't drink a whole lot. Okay. Yeah, soaps are actually bitter in taste, and at some point in our life we probably swallowed some. Okay, and so that's yeah, that's a bitter taste. And we don't usually eat bases in general anyway. Okay, so that's one thing, and then acids are corrosive and bases are caustic. Both of these two are burns, okay? They both burn you, whether it's an acidic burn or a basic burn, that's different. So they just have different terms to it so that anybody who's looking at that burn can treat you properly, okay? And if you remember in lab safety, the first week when you watched the video about spills and all of that, and hopefully your instructor showed you around the lab, I know I do, and then I show you the spill kits there. The spill kits are for acids and bases, okay? Because acids and bases have to be treated differently, okay? Because chemically they are different, so they have to be treated differently as well. So even the doctor would like to know that if you're having a burning sensation, that is it an acidic burn or do you have a caustic burn, okay? So that they can treat it properly. All right, and then other properties over here, which is not so much for acid, it's a little bit more for base, is that these are actually slippery to touch. And this goes right along with the soap thing, okay, is that the soaps are all slippery. And even in labs, when you start encountering bases like sodium hydroxide, and again, we don't touch, we don't taste any chemicals, okay, in lab. But if you do have an accidental spill on your hands for bases, you will realize that they're a little slippery, okay? And the strongest base that you encounter at your home, okay, ever, the strongest base will be what we call lye, which is the drain openers, okay, yeah. You want to clog the drains, the liquid plumbers and all of those. That's the strongest base you will actually encounter. Okay, other than that, ammonium hydroxides, which are your regular window cleaners, those are very mild bases. Okay, they're not very strong. The strongest acid you actually carry with you because it's in your tummy. That's the hydrochloric acid. Okay, and that's very strong acid. And the other acid we talked about before was the sulfuric acid, which your car carries, right? It's in the battery. So you do find a lot more acids in your life than bases, but they're all there. Anyhow, examples of all of these, you have enough of the examples of acids and bases, right? Hydrochloric acid, sulfuric acid, nitric acid, and bases would be all hydroxide bases. And most common one, simplest one to write is hydrochloric acid plus sodium hydroxide. Don't wait for me. Go ahead and write out the formulas. Both aqueous. Am I wrong or does that create water? Yeah, okay. You're not wrong. No, you're not wrong.
And because NaCl can both be both a solid or a liquid, would it, or aqueous, would it be aqueous or would it be solid?
Can NaCl be solid? Anyone? No, because sodium's in the first group. Okay, so the same rules still apply because you're working in an aqueous condition over here. So as soon as you form NaCl, you know it's going to be aqueous. Okay, because they are soluble in water. And then the other product that you form is HOH, which you can write as HOH if you want to, but really it is H2O. Okay, but if you feel like writing as HOH, that's totally fine with me. And HOH or H2O now, that's going to be liquid. Okay, however you write it, it's going to be a liquid. Yes, Dick.
When you add acid and bases, you'll always get water.
Yes, very good. That's my next step. Okay, so the general theory is that acid plus base gives you what we call salt and water in general. Okay, and that's why you need to know how to treat these things also, because if you spilled an acid, you will throw a base on it, and if you have a base, you will throw an acid on it. Generally, we don't do either. We throw water on everything. Okay, so but in general, if it was something dilute, then sure, we can treat it easily. This reaction also you're going to do in the lab, and then you will see why we don't do the opposite, which means that if we have an HCl spill, if you have hydrochloric spill, it's not a good idea to throw sodium hydroxide on it because it's a very exothermic reaction. Okay, and so if you generate a lot of heat, then you have to start controlling that part also. Okay, in there. So yeah, too many issues. So much better to just go ahead and dilute it with water, and that's how you get rid of it.
Would a grease like grease, would it be considered either an acid or a base or not?
Grease?
Yeah.
Grease is a totally different thing. Yeah, it's not even an ionic compound actually. Grease are fatty acids, okay, and fatty acids are completely molecular compounds. Okay, yeah, they're very different. Okay, very quick. Let's do the ionic equation here. H plus, aqueous, Cl minus, aqueous sodium plus aqueous hydroxide. Luckily everything is 1 and 1, so we don't have to worry about coefficients. And A plus aqueous, write fast. Cl minus, aqueous, and then H2O liquid. I know. What, you're still on? And then if you do write fast and you're already ahead, go ahead and write the net ionic equation. And we will cross out the sodium and the chloride on both sides. In general, for acid-base equations, your net ionic equations are always going to be this, because your acids will always have protons, your bases will always have hydroxide, so you always form water. Okay? All right. We're not done yet. We'll do a little bit more of acid-base next time, on next week.